people, and wish you the best.
People live in systems, and we create systems. I was just thinking about election today. Yesterday, I guess there was an election here in Massachusetts and many other states. And when you think about the U.S. government, it's really a pretty well-designed system. Here we have 3 branches of government, and in some ways they are fulfilling independence of functional requirements. 3 important functional requirements of government are fulfilled by executive branch, judiciary, and Congress. And I think that was a pretty good design. And in old days, one king used to run the country, and I'm sure it was a highly coupled system, and therefore perhaps they were not very efficient. Schools are systems, machines, software, and so forth. We create all this. And in fact, some of the things I did at KAIST was simply applying XML design to a university system. When I was at NSF, that's what I did, apply XML design to government organization. And that worked, in my opinion, worked quite well, although there are people who dispute that claim. So all the systems must be designed, they must be optimized, they must be operational, they must be improved, and we have to do all of these things without harming people, environment, and so forth. So it's quite a tall order to all these things. And in many cases, engineering schools have spent great deal of time to do the second one of these well, optimization well. They spent great deal of time to teach people how to model, optimize, which is very much needed. I think the reason people used to do that is because in old days, people who invented the system were not engineers. They were just people, medical doctors and others. They invented things, and then engineers were brought in to optimize. In fact, much of defense work was done like that. Defense contractors or people in Defense Department conceive these major weapons systems and typically use university professors to take a subcomponent of their system and then improve and then optimize. So engineering schools never developed the capability to design, and that I think is the reason why many universities are not effective in teaching design, and they should improve it. There are a number of systems that we need to develop. One of them, I think, has to do with conversion of CO2. And I will not elaborate all this. Saudi Aramco and KAIST made an agreement to spend $5 million each for 6 years and see if they can convert CO2 into some other useful material instead of storing CO2 under the ground. The idea was to convert CO2 into some other useful material that we can use. So we just signed a contract before I left KAIST. And so these are some of the many problems that we need to solve. And we talked about the batteries during the reception. People are using lithium battery. But can you imagine if we make enough batteries to propel all the vehicles in the world, we'll be running out of lithium. Do you know how much you have to pay for lithium then? And there are other safety problems and so on and so forth. But anyway, there are all sorts of issues that we need to deal with. So I say academic institutions should do a better job in teaching our students how to design, because after all, everything begins with design. Everything else follows the design. You have to have a design first before you can optimize and so forth. And I use this bimodal. I say we need to educate more people who are bimodal. Bimodally, what I'm trying to say is that engineering consists of analysis and synthesis. We need people who can function in these 2 domains of knowledge, both analysis and synthesis. And very few people can do this. WPI may be an exception. But in many engineering schools that I know of, I'm familiar with, most professors analyze. They model and analyze. That's how they were taught. That most of the professors got their doctorate degrees analyzing some small subset of an engineering system, and that's how they got their doctorate education. And one of the problems is that when people who teach at universities, engineering schools, are primarily analysts, people who are not interested in design, this entire educational process gets skewed. So we continue to have a difficulty in educating people who can be bimodal. And this, I think, is an important educational issue, and there's a challenge in being able to do this. At WPI, some of you who are from overseas may not know about WPI. So let me say a few words. WPI was well known because it had a unique education program. It had let students learn by having projects, and still I see that project-based education is emphasized here. But maybe 20 years ago, 30 years ago, WPI education program was very, very unique. And my understanding is that it took too much of professors' time to educate students that way. Therefore, they didn't have time to write papers and whatnot. So I think they modified it a little bit. And I was sorry to see that WPI changed its educational system because it was unique, was needed, and was very appropriate. But then university professors have a lot of pressure to publish papers and this and that, get grants. So I can also sympathize with why they changed it. In my case, I was very fortunate. I got my undergraduate education at MIT, but by accident, I had to earn my own way through MIT. So I had all kinds of jobs while as an undergraduate student. And after my junior year, I had this job in a very small company. I was the only engineer in the company. There were the rest of them were machinists and operators of extrusion machines and so forth. So I was an engineer. Before I had the title of development engineer after my junior year and worked at company for 3 days a week. I studied at MIT 3 days a week during my senior year. And I developed the thing because a company president had this idea that we have to have this kind of product. And he talked to me about developing some product. He didn't know what. But he said, this is where the market needs are. We want to use some of our products in vending machines, and then so on and so forth. So I created this new process, new product, and so forth. That was a very important education. In fact, that sort of oriented my thinking about engineering. And I got a patent on this. But the interesting thing is I could not submit that to satisfy the thesis requirement at MIT. They would not just, the idea that the work I did at the company, which is a significant piece of work, company made a lot of money, and this is made in billions, yet I could not submit it to satisfy my thesis requirement, undergraduate thesis requirement at MIT. I had to do another thesis, which was a trivial thing. I tabulated some numbers for one of my professors, and that was my bachelor thesis. Yet that was acceptable, but this kind of thing was not even considered, as I didn't have dare to ask my professor if I can submit this to satisfy my thesis requirement. But the point of the whole thing is that universities have certain orientation, and they do. If someone comes out with a very good design, and therefore one can optimize it very simply, because design is so good, that's the case. If you have a good design, as all of you know, you don't need fancy analysis, because you can optimize it, you can satisfy requirements very easily. That's the nature of a good design. But if you have that kind of design, sometimes people say, how can this be a doctoral thesis? It's so simple. It's simple because the design was done so well. Yet universities just don't recognize that. And this was the case at one of the promotion cases at MIT. And one of my colleagues objected to promoting somebody, saying that this paper here is, this cannot be a scholarly paper, not too many equations, no many curves and all this. And I had to remind him, that's because he had a very good design. He synthesized a solution which was very good, and therefore he did not need all these hours of computer simulation and all that. And so this something is not quite right in terms of engineering education. I did the same thing in another company, USN Corporation. After working for a small company, I decided to work for a large company. So I joined the company. And again, they had a very complex problem. And they took many years trying to solve it. They couldn't solve it. And when I looked at it, it was a very straightforward problem. And so again, it turns out that they are functionally independent. The only thing I did was there were 3 functional requirements. I satisfied them by coming out with the design. That's uncoupled design. And at the time, I didn't know it was uncoupled design. All I knew was that came up with a solution. So the point is, many professors nowadays do not have industrial experience. And therefore, they do not have to confront these problems. And so sometimes, since they got their doctorate degree doing analysis, they do not appreciate the important scope of that engineering design plays in universities. How did I get into LMP story? You might be interested in a little bit of this story. Again, it tells you a little bit about university. Since I have a President Ryan here, I thought maybe it's more of interest to him than to anyone else here. I was asked in 1976, I was asked by MIT to create interdepartmental laboratory in the field of manufacturing. They made a study, they had a committee, and the committee recommended that such an organization be established. But for a couple of years, nothing happened because no one was willing to undertake the task, and it was somewhat controversial. So they asked me if I would organize such a thing, and they gave me $20,000 and 50% of one assistant professor and one associate professor's time. And they gave me a title saying that I'm the director of interdepartmental laboratory. They gave me a hunting license. And this was a very troublesome thing in some ways because my professors at MIT, Milton Shaw, had to leave. Chris Brown knows him quite well. He had to leave MIT because he was a full professor, tenured professor, well-known, international, well-known professor, but he was in the field of manufacturing. When funding went up, MIT thought that kind of field should not be taught at MIT. They said MIT should be in engineering science. Forget about manufacturing. So he ended up packing up and going to Carnegie Mellon as head of department. And this story you will not hear from anybody else other than me, I guess. And that's actually how I ended up at CMU. So when I was asked to create this interdepartmental laboratory at MIT, I said, and after kicking Milton Shaw out, now they asked me to create this. And I said, what was wrong with what Milton Shaw did at MIT? Milton Shaw was a famous scholar. He got all kinds of honors and so forth. One thing that was very clear, having been his student, is that much of his work was based on experiment and a lot of trial and error kind of research. In fact, because the research required trial and error processes and whatnot, some of the things he taught us were not quite right. After 10 years, 15 years or so, we found that that's not always true. In fact, many things I learned as a graduate student turned out to be not true. So that's when we decided that what MIT should do by creating this new interdepartmental laboratory is create a science base. So I said the goal or the purpose of LMP is to create science base. Then people start asking me, how do you create science base? I didn't know. But I said that science base got to be there to advance the field of design, manufacturing, and so forth. So I wrote a proposal to NSF because I needed money. I got only $20,000, and they were asking me to create a new interdepartmental laboratory at MIT. And I needed a lot of money. So I wanted to go to NSF and ask for a lot of money to create that kind of entity. So I called it axiomatic approach to manufacturing. In contrast to algorithmic approach to manufacturing. Algorithmic approach would be, if you follow certain sequence like a software, you get the right answer, right? In axiomatic, but that wouldn't work because you cannot generalize. To generalize our understanding of something, it had to be axiomatic. That's why axiomatic design was created. To generalize what we know such that we can teach students and we can practice it. And this is the beginning of it. So I went to NSF, and then I submitted a proposal. I needed money, so yeah. So I went to NSF with a proposal that I'm going to create axioms for design. My colleagues at MIT were very negative. Design professors, I was not in design group, design professors thought design can only be taught based on experience. There is no theory. So MIT Mechanical Engineering Department did not have any graduate courses in design because they believed that design cannot be taught. So my argument was, if it cannot be taught, why should students come to MIT? Why don't they just join a company? So in any case, I wrote a proposal to NSF. And then I went down and talked to the program director, you may know him, Dr. Bernie Chern. I went to Bernie and I said, previous to this, I got a big chunk of money from NSF for the MIT Industry Polymer Processing Program, large amount of money. So I said, Bernie, I need some money. And I showed him this proposal. And he looked at it, just a title. Initially, I mailed it to him, and then I went down to Washington. And he looked at it, he said, this will never get funded. It's such a crazy idea that you want to create axioms for design and something like that will not fly. But he was very nice, he was very kind. He said, instead of circulating, mailing your proposal to 3 or 4 university professors, in which case you'll get F. F means the lowest grade, not the F. And then you'll never get funded. He said, instead, I'll bring reviewers. I'll select 6 academics and 6 industrial people and bring them to MIT, and you explain to them. Then perhaps you can convince them. So I did that, and he arranged it. And just one day before they came to MIT, one of my colleagues who was working with me to develop this lab said, here, I met one of the reviewers coming tomorrow, and he said, they cannot argue against the idea of creating axioms, but proposal doesn't talk about how to create axioms. There's no word about how to go about creating axioms. So based on all these things I did at Guild Plastics, USN Corporation, at MIT, and University of South Carolina, I came up with very quickly 12 things that seem to be common in every successful project. And I called them hypothetical axioms, and came to MIT, and I discussed this with my colleagues, two of my colleagues, and then we reduced 12 down to 6, and we called it 6 hypothetical axioms, the other 6 corollaries. And they are still written in the book that way. The following day, we made a presentation. They were really excited. We spent a whole day talking about this. This is how axiomatic design got funded, and this is how we did this. The reason I'm saying all this is because at universities, sometimes you don't have funding and whatnot. You cannot get new ideas started because not only it's difficult to start new ideas, but there are so many people who oppose the idea, who think it's impossible, that it's hard to do. I'll show you another video clip that on online electric vehicle that President Ryan talked about. And same thing. For some reason, when you propose a complete new idea, everybody is against you, oppose it, saying it cannot be done and so forth. Maybe that's the way it is at the university. But anyway, we need to change that. So I want to show you a video of Olive, and you may find it interesting.
Lighter, freer, safer. It runs for the future. A new open leading electric vehicle based on KAIST's convergence technology. The global green innovation, OLEV. The new green automobile revolutionizing the world, KAIST's open leading electric vehicle. This vehicle is the first of its kind that is powered wirelessly, whether it is stationary or in motion, through a power grid embedded under the road. KAIST's OLEV charges itself on the road, and it consumes 1/5 of the battery power of comparable electric vehicles. This resolves some of the issues that have prevented electric vehicles from being commercially viable, which include battery weight, price, and limited driving range. In addition, KAIST's OLEV is emerging as an effective and economical model in the face of environmental restrictions and the current energy crisis, since it doesn't require the construction of expensive charging stations, nor the typical 10-hour charging time. KAIST's Convergence Research Center developed the SMFIR technology for the first time in the world. The SMFIR is shaped magnetic field in resonance technology, which safely delivers high amounts of energy to an electric vehicle while it is stationary or in motion. With this technology, power is transferred from the ground to the bottom of the vehicle, 20 centimeters apart, while maintaining power transfer efficiency at 80%. Also, with up to 100 kilowatts of power supply, the technology brings OLEV much closer to its commercialization. In addition, OLEV distinguishes itself from previous electric vehicles in terms of safety and convenience. The wireless recharge mechanism eliminates any risk of electrocution, and the electromagnetic shielding technology drastically reduces electromagnetic radiation to levels much lower than international standards. The power lines are managed by segment control technology, which supplies power to the vehicle only when it is passing over the lines. This technology prevents a magnetic field from being generated while pedestrians walk or other vehicles run on the road, as well as the wasting of energy. As only 20% of the total tracks, including acceleration segments, crossroads, stops, and parking areas, need to be equipped with power lines, KAIST's OLEV is much more economically feasible than previous electric vehicles, which require large capacity recharging facilities. KAIST is striving to open the future for the commercialization and globalization of the open leading electric vehicle. By starting commercial service in the circular line of the Seoul Grant Park, the eco-friendly open leading electric tram further boosted its potential as a future green car, and the open leading electric vehicles are expected to be applied in bus-only lanes. Following the commercialization of the open leading electric tram at the Seoul Grant Park, open leading electric bus pilot projects will be promoted in the cities of Seoul, Daejeon, Sejong, Jeju Island, and the Expo 2012 Yosu, Korea. We're also collaborating with various international cities that want to adopt our green technology. These include the Enstek Green City in Malaysia, Park City in Utah, and Boston's Logan Airport. By solving the technological limitations of previous electric vehicles, KAIST's open leading electric vehicles have brought down vehicle and recharge infrastructure costs to affordable level. They provide a revolutionary means of transforming our current transportation system into a green and eco-friendly one, especially as we face the energy crisis with the decrease in crude oil imports. We also aim to strengthen our position as a technologically innovative country, where our core source technologies can generate patents and license-related revenues from other countries. Aside from its inherent value as a core source technology, continued investment in the OLEV will allow the SMFIR technology to be applied to other fields. Through continuous research and development, we will make the arrival of a carbon-free future faster. A new generation of green technology that has ushered in the future of electric vehicles. We're driving toward a clean and green future. KAIST, open leading electric vehicle.
There are a couple of things that should be noted here. One is it took only 2 years from the date that we started the project. 2 years later, we implemented it with passengers around Seoul Grand Park. In fact, today, that system in Seoul Grand Park is making money. Not a whole lot of money, about $400,000 a year. And the system will be installed in one of the industrial cities called Gumi starting next month. So I think they will start running in July. And also this technology is being developed to be used in high-speed train. By the way, this road does not have this underground thing in the case of bus system everywhere. It has only 16 to 20% of the roadway has this. The rest of it runs with a battery. And the battery is recharged. So when it makes one round, charge and battery remains the same. Just it depletes a little bit, recharge it, and so forth. So if you start with a 50% charge, when you make one complete round, it remains at 50%. This is how the roadway is designed. In the case of a train, we'll do the whole thing. We are now developing, I shouldn't say we, because I'm no longer there, but we've been developing a train that will go about 300, roughly 300 miles per hour. The high-speed train runs at about 300 kilometers an hour right now. And we are trying to up it to about 50% higher, so to run about 450 kilometers an hour. The reason we can do that is we eliminate this Y on the top, which limits the maximum speed you can run at. So by eliminating it, by supplying it, in the case of rail, it's very simple because it just moves in a fixed direction. So that's the idea. They demonstrated indeed they can transmit 1,000 kilowatts of power while I was there. And then now they are, after I left there, they showed tram. So there's like a streetcar with the rail, but no wire anywhere. They'll be all coming from underground. And that will be installed in a few cities and so forth. So in Korea, it's going very well. In the US, I'm trying to see this gets adopted. And lots of cities are interested. And the financing is a problem. So in doing this, we have so many functional requirements. I wrote down about 8 of these. And one of the difficulty in designing something is, first of all, coming out of the functional requirements. After you come out of the functional requirements, there are so many design parameters you can use. Question is, which ones do you select so that there will be either uncoupled or decoupled design? No mathematics will tell you how to do that because it just cannot. That's where the first axiom and second axiom plays a role, because only by using these axioms you can begin to choose right DPs, design parameters. A lot of people think that you can somehow manipulate matrix and come out with the optimum design. But matrix will not tell you how to choose which design parameters one ought to use. In fact, design axiom tells you that number of FRs, number of DPs got to be the same. very important thing, but lots of people just, when you try to do it based on experience, you just forget about all those things. So there you can come out with the DPs, and then we had to one of the major problems was sending the power from underground cable to the vehicle, which is about 30 centimeters, because underground cable is about 10 centimeters below the surface, 30 centimeters. So how do you do that? And this is where the power of XMA design came in, right? So we want to transfer large amount of energy and control power level and catch the power from the vehicle. By somehow, the vehicle must catch the power. The question is how you do that. A couple of things we know, right? One is you need 3 design parameters, right? The question is, what are the 3? Turns out that very simple. The distance that you have to send this power to will be determined by the distance between the poles, magnetic poles. Let me show you this. So this is a pictorial thing. It's not really done exactly this way, but pictorial thing. We have 2 poles, right? Just like an Earth magnetic pole, North Pole, South Pole. Because we send the electricity and we convert it to magnetic field. So we have 2 poles. If the poles are very far apart, magnetic field shape is going to be higher, right? If it's narrow, it's going to be like this. So you can reach 30 centimeters, whatever, by changing this, right? And you can change the strength of the field by just sending different amount of current that generates magnetic field. And you catch it by using resonance, so that impedance and frequency got to be right, so you catch it. Essentially, all you do is change the capacitance to be able to do that. Very simple idea, right? Very simple, not very complicated to implement and so forth. That's why we could do it in 2 years, go from idea to implementation. Turns out that this is not the only project which we could do in 2 years. A lot of other projects. We created a mixed alloy, same thing. Mu cell, it took a little bit longer, but my graduate students worked on decoupled the materials processing system, and they did it in a very short time. Over and over and again. And many people, when I went to NSF, they said, you cannot change government agency in the time that you'll be here. But in 3 months, we changed it. We got approval of Congress, we got the budget redone, and so on and so forth. 3 months. Because once you present what you're going to do in a very systematic way, people did not object. OMB did not object. Congress did not object. So whether it's a machine or a system, very systematic, logical way of thinking is very important, which is what design is all about. And this is, I'm not going to dwell on how it works. And so what XMA design teaches is how to create appropriate system solutions, how to define FRs from customer needs, how to choose set of DPs from many possible sets, which is very, very important, right? And it also tells you that we only need exactly the same number of DPs as FRs that you have, and tells you how to improve the performance system, and then how to make use of reinitialization of the system to make system last longer. And some of these are written in the complexity book, how to decompose, and how to create system architecture, and so on and so forth. So this is why this was created. And initially, I had a real problem with some of my colleagues who were design specialists. They were really unhappy that I wrote a book, and the name of the book is, I use the principle of design. And they say, how can you put the principles of design? You should just call it principles of design. Eliminate the, but anyway, the book already was printed, so I could not change it. So, and when we did this online electric vehicle, surprisingly, all electrical engineering professors opposed it. And high electrical engineering professors would not participate, saying they cannot be done. Professor at Seoul National University, who is the director of the electric vehicle thing, opposed it, and not only that, he went around everywhere using politicians to cut off our funding and so forth. It's all electrical engineers who said it could not be done. Because they said the most you can jump over empty space with the electric power is about 2 centimeters. I couldn't explain to them that we are going to use field effect. And because of patent situation, we couldn't explain. So for 2 years or so, all the time we worked on it, they really made our life very difficult. Each time government reviewed our project, they somehow became a part of the panel and gave us a flunking grade every time, and so on and so forth. It's an interesting psychology. They should work on their own ideas of project rather than opposing what someone else is doing. We spend a lot of money. I think that's part of the reason. By appealing directly to the Blue House, which is equivalent to White House here, first year we got $25 million for this project, $25 million for mobile harbor project for 1 year, 7 months. Altogether, we spent roughly $50 million on online electric vehicle and about $40 million on mobile harbor. And their argument was that, gee, instead of having KAIST all that money and spent on 2 projects, he could have supported 1,000 professors, each getting $50,000 per year. And they thought this is a waste of money. But in any case, this is part of the problem when you try to do something new. An instinct is that people oppose what you're trying to do. So the purpose of XMA design is create something new. So every one of you will run into this problem. People telling you it cannot be done because it's new. It's not because they have any ill intention, but simply they just cannot imagine such a thing can be done. And another thing we did was mobile harbor. Instead of building a large harbor, we said big ships should remain in deep waters and harbor should go out to the ship. It sounds like a crazy idea, right? Again, we demonstrate that idea in 2 years. Very short time, right? So I think this kind of thing should be taught to students, industrial engineers, and so forth. KAIST, I organized KAIST based on XMA design. I didn't talk about XMA design to my colleagues, my professors, because they're opposed, right? So, but that's how it's done. Design what KAIST should achieve, and to achieve that, I came up with DPs for KAIST, and I implemented for 7 years. That's all I did. We followed the thing that we designed without making many changes. And President Ryan talked about KAIST ranking coming up. In fact, in engineering, some parts of engineering is at the same level as Caltech, in top 20. That's pretty good, right? And overall, it doesn't have schools of humanities. It has only engineering and science, more or less, a very weak liberal arts areas. And yet, its ranking came up from somewhere around 196 or so to this year 63. That's pretty good, right? Jumped very, very fast. And that's because everything was done very systematically based on XMA design. And so it's not just a matter of talking about doing this or doing that. We set the goal, we came out with the DPs, and systematically did it. And then I had to raise money to implement all this. You need money, by the way, right, to run a university. So I hired 350 new professors, increased faculty size by 50%, and built 14 new buildings in the time I was there. And it made a lot of people uncomfortable because everybody had to adjust and change. One of the problems, as I say, is universities are not teaching it. And it's because of the current reward system at the universities. Universities are counting number of papers, grants, and so on and so forth, and somehow prevents professors from daring and do things that appear to be difficult or impossible to do. And since universities are populated with people who are more interested in analysis, universities do not have these bimodal thinkers, And therefore, they form a culture they tend to reject that does not quite fit their own culture. And that's why universities are very difficult to change. With lots of tenured professors opposing some changes, it's a very difficult thing. And yet it had to be done. And not easy. It's not a popularity contest. So many people try to do by try and error. And in view of time, I'll just do not dwell on all this. By using XML design, you can do things fast because you don't make mistakes. You know, just like driving nails into the wall. If the nail bends, then you have to take it out and do it. In industrial operation, if you make a mistake, if you have to remake mold, say, if you make a tool, it will take you 6 months. Just to remake it, try it again, right? So if you try 3 times, then you'll waste a year and a half or 2 years, right? That's why industrial firms spend years and years to develop something new, because they make a lot of mistakes along the way. They think it's natural that people make mistakes, and they tolerate it, because that's the only thing they know. And so these are the things that we should avoid doing it. So let me I talked about some of these. So we think this can have many, many different applications. We can have appliances at home without any wiring, right? You just have appliances anywhere in the room. You can deliver power to it. Right? So you don't have to have all these plugs, right? This high-speed train, no overhead cable, and so on and so forth. And this way, if we can generate electric power without burning hydrocarbon, we can reduce CO2. That's why we did it. The reason I thought about this project is we want to reduce CO2 level, because my assumption was that for KAIST to be famous, it has to solve a problem that humanity needs to solve in the 21st century. So it's obvious. One of the problems we have to solve as a humanity is CO2 problem. So I said, we're going to solve that. And one way of solving it is not have internal combustion engines running in the cities. So let's get rid of internal combustion engines. How do we do it? We have to go electric. And this is the kind of the reasoning process we went through. And this is why we started working on it. We did not say, let's work on OLED just for the sake of it. We started tackling this because we wanted to contribute solving important problems of humanity in the 21st century.